Hello, my name is Dr. Snyder. Today we will be covering electron configuration. We will be able to identify the probable placement of electrons while an atom is in the ground state, recognize the pattern in which electrons fill orbitals within a sublevel, be able to identify the electron configuration for an element, and complete an orbital filling diagram. So here we go. Electron configuration is the arrangement of electrons within an atom. Here are some orbitals that I found from the textbook that we use in our classroom. As you can see, these orbitals have different shapes. The s orbitals have a round or a spherical shape, and then these, I often hear them referred to a dumbbell shape for the p orbitals. There are 3 p orbitals in the x, y, and z planes. We also have our d orbitals listed here. Here is a set of orbitals that fit in the first and the second energy levels. You can see how they go together and so forth. With the Aufbau principle, each electron occupies the lowest energy orbital that is available when it's in the ground state. This shows that an electron will fill the first energy level when given an opportunity. After the first orbital is filled, or the first energy level is filled, then the electrons are pushed out to the second energy level, the s sublevel, and then the p sublevel of the second energy level. After those are filled, if it's in the ground state, then they will be pushed out to the third energy level, the s sublevel, and then the p sublevel. And if you notice, we do have a 3d sublevel here, but it is slightly higher in energy than the 4s. So after the 3p is filled, then the electrons go to the 4s, then followed by the 3d, then the 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, and then 7d. If we fill all of these orbitals, that takes place of 118 electrons, and that's pretty much all that we'll ever need to use. As these orbitals fill, the electrons will go from the lowest energy state to the next lowest energy state. Pauli's exclusion principle says that a maximum of 2 electrons can occupy a single atomic orbital, but only if the electrons have opposite spins. We can represent the electrons and its direction of the spin with the arrows. So as we go with this orbital filling diagram, we can liken it to these magnets that I have right here. I've just simply got this pencil to give stability to these magnets. We're going to pretend as if the gravitational force given by the Earth is the attraction of the nucleus of the atom, and these magnets will represent electrons. So this first electron that we place, or this first magnet that we place, is going to be attracted as close to the gravitational force as it can. So it will go as close to the ground as it can. And then as another electron comes in, or another layer or shell is filled in, if we notice, this series of electrons desires to be as close to the nucleus as possible, or as close to the gravitational force of the Earth. As it does so, we see a levitation. And so this allows us to get a difference in our energy levels. If I increase the energy levels, so to say, or increase the amount of electron or shells that I fill, I can add a third layer of electrons. Once again, these electrons are able to repel each other, yet still be attracted to the nucleus. And I can continue to layer these on, and if I were to remove an electron or move an electron because I add energy to it, we notice how that affects everything. And once that energy is released, that energy will fall back to, or the electron will fall back to the ground state. Okay? With Pauli's exclusion rule, a maximum of 2 electrons can occupy a single atomic orbital, but only if the electrons have opposite spins or spinning in the opposite direction. We can represent the spin of the electrons with arrows. Hund's rule, also known as the school bus rule, says that electrons will not occupy the same orbital unless there is no other option. If you think of a school bus, if the school bus only has 3 seats, I know that's a small bus, but if a school bus only has 3 seats, the first person on the bus finds an empty seat. The second individual on the bus finds an empty seat as well. And then the third person, once again, finds an empty seat. But if you are that fourth person, you are forced to share with somebody. The fifth person, once again, is forced to share that bench seat. And then the sixth person will fill all of the seats and pair them up. And that is why we call it the school bus rule. So if we have 2 electrons that share the same orbital, those electrons are labeled as being paired. If an electron is all alone in the orbital, it is labeled as being unpaired. Seems simple enough. The electron configuration, as I previously said, gives us the probable location of each electron in an atom. And in this configuration, it consists of energy levels. As we currently have with our periodic table, we have energy levels of 1 through 7, each being represented by the rows of the periodic table. The sublevels that we use are the S, the P, the D, and the F sublevels. There are other sublevels available, but they are not utilized within a normal setting. The orbitals can have 1 orbital for every S sublevel, 3 orbitals for every P sublevel, 5 orbitals for every D sublevel, and 7 orbitals for every F sublevel. Each of these orbitals can have a maximum of 2 electrons within it. Once again, they must be spinning opposite directions if they are in the same orbital. Since we have 1, 3, 5, and 7 orbitals in the S, P, D, and F sublevels, we may have 2 electrons in every S sublevel, 6 electrons in every P sublevel, 10 electrons in the D sublevel, and 14 electrons in the F sublevel. Once again, if an electron is paired, they must travel in opposite directions. So here's a breakdown of how the numbers are listed. I've got a large number there, and let's just call this number 3 for energy level number 3. And then next we list our sublevel, which we can identify as either a sublevel or we can recognize it as a block on the periodic table, depending upon the method that we want to use to find our electron configuration. The next would be the number that is in a superscript position or a position in the upper right portion. And that can either be found by the number of electrons in that sublevel or based upon the column number within the block of the periodic table. I will teach you 2 methods in order to find the electron configuration, and these are representative of the 2 methods. Go ahead and pause the tape and write this down in your notes. So for our electron configuration, the first method that we will use, when I was in high school, we called it the Christmas tree method. Now I call it the old school method. If you write down on a piece of paper this portion right here, make sure that you are symmetrical in your columns and in your rows. If you wanted to write, for instance, the electron configuration for chlorine, you can identify that chlorine is atomic number 17. And if it is neutral, or in the neutral state, it will also have 17 electrons. Therefore, we would identify it as the same number of electrons as protons, since it is in the neutral state. In order to find it, I must first start with the very first energy level, or the lowest energy state. And that first energy level can hold 2 electrons, and it will fill the S sublevel. We would write that as 1s2, that first number being the energy level, the S being the sublevel, and the 2 being the number of electrons within that energy level. The next set of electrons would be pushed out to the second energy level. And so we would list that as 2 for the energy level, S for the sublevel, and once again a 2 in the superscript position to represent 2 electrons within the S sublevel. Next, we would see the P sublevel being filled in the second energy level, in which we would have the 2 to represent the energy level, the P to represent the sublevel, and the 6 to represent the number of electrons in the P sublevel. Following that would be 2 electrons to go into the third energy level. That would show us 3s2, 3 for the energy level, S for 2, S for the sublevel, and then 2 for the number of electrons within that energy level. Therefore, this would have a configuration of 1s2, 2s2, 2p6, 3s2. This would be the electron configuration for the element magnesium. Now, if we were to continue to go forward and find the electron configuration for chlorine, we still need to find 5 electrons. We have the first 12 found, and now the last set must be pushed out to the third energy level, P sublevel. We don't need to place 6 electrons in there because that would give us 18 electrons. We only need to place 5 more. So we would simply write 3p5 for that 5th set of electrons. If we count all of these up, we actually have 17 electrons. We have 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 5 is 17, to give us all 17 electrons. Okay? Now go ahead and pause this video once again. Make sure that you have this written down. As you notice, we do have some energy levels that are not used. We do have a 5G, 6F, 6G, 6H, as well as 7D, 7F, 7G, 7H, and 7I. Once again, these are positions or orbitals and placements that electrons have the ability and the opportunity to go to. But at 118 electrons, we do not utilize those spaces, but they still exist. And the rest of the chart would be filled out just in this sequence, as we see, starting in the upper right portion, going to the lower left, and continuing down. And there we go. Electron configuration for chlorine is here. If we were to excite the electrons, as we have with this pencil, if I were to excite the electrons and add energy of some sorts, be it heat, be it electromagnetic radiation, be it mechanical, whatever the force may be to excite that electron, I can move this electron out, and therefore it would have a different configuration because the electron is located in a different spot. We would still have the same number of electrons unless we supplied so much energy that we removed the electron from that atom. But if we only supplied a little bit of energy, that electron would still be intact with that atom. And we may have an example such as 5 electrons in the outer sublevel, those being excited and therefore having a change so that 2 of the electrons jump out to the 4th energy level, S sublevel. Once again, we still have 17 electrons. And this happens when the correct frequency or the correct amount of light reaches that electron and allows that electron to jump to a different sublevel or an energy level. Now, valence shell. Valence, as I've told you in class, means outermost. And so the valence shell will be the outermost shell or the outermost energy level. The outermost shell is going to be the 3rd energy level for this example of chlorine. If we want to find out how many electrons are in the outer shell or in the valence shell, we are simply going to identify what is our outer shell. In this example will be 3, and then we will simply add the superscripts. 2 plus 5 is 7. Therefore, we have 7 valence electrons for this example. All right. And so here's the maximum number of electrons that we can have in each energy level. In the first energy level, we can have a maximum of 2. If you notice, there are 2 elements in the second row, or in the first row. In the second row, or the second energy level, we can have a maximum of 8 electrons. If you look at the periodic table, there are 8 elements in the second row. For the third energy level, the rules begin to change. We can have up to 18 electrons in the third energy level, 32 in the fourth energy level, 50 in the fifth energy level, 72 in the sixth energy level, and 98 in the seventh energy level. Those are the maximum number of electrons for each energy level that we use. Here's an example of the periodic table. Make sure that you note that this element right here, helium, is actually a part of the S block, and therefore we will notice that it can move to this other position over here. And here's another example of how to do electron configuration. As we go through this, we can notice that we have our first row, once again with helium located over here in the S block, right next to hydrogen. The electrons would enter in the lowest energy state possible, and that would be the first energy level. Next, the electrons are going to go to the second energy level, working from left to right. After the second energy level, then the next set of electrons fill the second energy level, P sublevel. We can hold 6 electrons there. Once again, because in the P block, we have 1, 2, 3, 4, 5, and 6 columns. After that 10th electron, then all of a sudden we must jump out to the third energy level, S sublevel. We can hold, once again, 2 electrons there. So that finds the electron configuration for 12 electrons. For the 13th electron, we have to jump out to the third energy level, P sublevel. Once again, that can hold 6. After we have that, that is a total of 18 electrons that we have found a home for. For the 19th electron, we must go to the 4th energy level, S sublevel. We can hold 2 there. So now we found a home for 20 electrons. This is where the rules start to get a little confusing if you utilize the periodic table method for identifying your periodic or your electron configuration. After the 4s, if you notice, now all of a sudden we jump into the 3rd energy level of the D sublevel. There are 10 columns in the D block, therefore we can fit 10 electrons into the D sublevel. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Then we jump back out to the 4th energy level, P sublevel. Once again, 6 electrons can fit in there. So this would find a home for 36 electrons once we get all the way out here to krypton. After krypton, electron number 37 is going to be pushed outwards to the 5th energy level into this S sublevel. It once again can hold 2 electrons. And then the electrons dive into the 4th energy level, D sublevel, and then back to the 5p or the 5th energy level, P sublevel. After that, the 6th energy level starts to fill up in the S sublevel. And then, if you remember, the F block is actually positioned and squeezed in here. So after the 6s, we then go to the 4f. And then we fill up to 14 electrons in the F sublevel, and we can remember that because we have 14 columns in the F block. Feel free to pause this video and count it to verify it. After the F block is filled, then we go to the 5D, and once again we can hold up to 10 electrons. And then we're pushed outwards to the 6p, and then the 7s once again. And then back to the F block, 14 electrons will fill in. After those 14 electrons have filled in, then we jump into the 6th energy level, D sublevel, with 10 electrons. And finally, electrons number 112, 13, 14, 15, I'm sorry, I can't count today, 113 electrons, 14, 15, 16, 17, and 118 electrons is where we finish with our very last element containing those 118 electrons if they are exposed to them. So that is how we figure the periodic table method of the electron configuration. So here are some examples of the electron configuration. Go ahead and pause the video and write these down and try to identify them. And now you're back. For hydrogen, did you get 1st energy level, S sublevel, and 1 electron in the S sublevel? For helium, helium is in the 1st energy level, S sublevel, and 2 electrons. Lithium, the last, or all of the electrons, the first 2 electrons go as close to the nucleus as they can, so it goes to the 1st energy level, S sublevel, and 2 electrons. And then the next electron, or the 3rd electron, is pushed out to the 2nd energy level, S sublevel. As we continue, 1 electron at a time, going upwards and upwards. And silicon, and finally bromine. This one's much more of a challenge, but I think you can do it. So with bromine, we have our first 2 electrons being identical to what helium has, and then the next 2 being identical to what beryllium has, and 2p6 being identical to what neon has, and then 3s2 identical to what we would have for magnesium with 12 electrons. And 18 electrons gets us to 3p6, and then 2 more electrons, electrons 19 and 20, will fit in the 4s2, and then the electrons 21 through 30 will fit in the 3d10, and lo and behold, 4p5 is where we finish out with 35 electrons. Here is an example of a shortcut in writing these electron configurations, because they do get quite long with the larger atoms. Notice, with this electron configuration, we will use the previous noble gas. And so the previous noble gas for sodium will be neon. Neon has atomic number 10, and sodium is atomic number 11. So instead of writing the long form, we put neon in brackets and follow with whatever comes after neon, which will give us the sodium. And we continue down and go through all the way until we reach argon. We can write argon in this fashion, or just simply put it in brackets and show that we have a full p block. Here is an example of an orbital filling diagram compared to electron configuration. We do have our arrows representing the spin of the electrons. Each arrow is an individual electron, and the direction that the arrow is going will represent the spin of the electron. Each box represents an orbital. Therefore, we have a 1s box in which hydrogen has 1 electron and therefore 1 arrow. Helium, 2 electrons with 2 arrows. They occupy the same energy or the same orbital, therefore they must spin in opposite directions. And our electron configuration shows 1s, 2 electrons, 1s, 2 electrons. And we continue on with lithium and beryllium and so on and so forth. Feel free to pause the video and look through these. And now, as I show you with the periodic table, make sure that you list these items down as we have our blocks. If you have not previously done these items, I want you to mark the S block for my class. The S block are these first 2 columns. The P block are these 6 columns over here. The D block are these 10 columns in the middle. And the F block are these 14 columns at the very bottom. If you recall, the F block fits in between the S sublevel and are between the S block and the P or the D block, the S block and the D block. But for practicality purposes, we pull it out so that we can work more easily with this. This periodic table is given to us through ptable.com. And if you notice, we actually have the orbital filling diagrams right here with the arrows. We can start with hydrogen and also showing our electronic configuration, the expanded form as well as the short form right above it. So we have our first energy level, or 1s, 1s2, and then atomic number 3 for lithium, and so on and so forth. Notice how we have our electrons filling in. And then we can go to boron, carbon, 1 electron at a time. I invite you to go to this website. It's an excellent one that I use very often in my classroom. At this time, I want to go ahead and complete a few elements in an orbital filling diagram. So let's start with lithium. Lithium is atomic number 3, so I need to find a home for 3 electrons. If you already have this placed out, it will make it easier as if you do the orbital filling first and then the electron configuration. If I need to find a home for 3 electrons, I need 3 arrows. The first arrow is going to go in the 1s sublevel. And then the second electron is still in the 1s, and now that orbital is filled. So the third electron gets pushed out to the second energy level. Now that I've got a home for all 3 electrons, I can more easily do the electron configuration. Next element is boron. Boron is atomic number 5. And so, let's go ahead and do the electron configuration for lithium. I'm just simply going to write down what I have here in front of me. I have a 1s with 2 electrons, followed by a 2s with 1 electron. And now to boron, I've got the first electron and the second electron must share the same orbital and spin the opposite direction. Electron number 3, electron number 4, and the 5th electron is able to go in the second energy level, P sublevel. Once again, I just simply write down what I have. I have a 1s with 2 electrons. I have a 2s with 2 electrons, and then I follow it with a 2p with 1 electron. Next is nitrogen. Nitrogen is atomic number 7, so I need to find a home for 7 electrons. Once again, the first 2 electrons in the 1s, and then electrons number 3, number 4, number 5, and now I am forced to do the school bus rule. Electron number 5, electron number 6, and electron number 7. Once again, I write down what I simply see. I see a 1s2, 2s2, and a 2p3. And now, if I go to a more challenging electron configuration, let's do this one for lead right here. Lead is atomic number 82, so I need to find a home for 82 electrons. The first 2 go into the 1s, followed by the 2s2, and then, using the school bus rule, the next 3 electrons, and then I'm forced to pair them. Then the next set of electrons jump out to the 3rd energy level, and then 3s and the 3p is now filled. Therefore, we have to jump out to the 4s, 1 up, 1 down. And I get to then dive into the 3d, going up, 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 and up. Next will be down, 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 and down. And right there, that's 10 electrons within the 3D. After the 3D, now we're pushed out to the 4p. And we can have up to 6 electrons in the 4p. After that, the 5s needs to be filled. 1 and 2 electrons. And then the 4d, oops, there I go, messing up again. Great reason to use a pencil. And my 5 electrons all sharing are all going to available orbitals, and then my next 5 electrons being forced to share. And now I have found a home for 48 electrons. And then the 49th electron, 50th, 51st, 52nd, 53rd, and 54th electron right there. And then I go to the 2s2, there's 2 electrons. And then I jump to the 4f, in which I have 1, 2, 3, 4, 5, 6, and 7 electrons there. Now each orbital is filled with at least 1 electron. Now I'm forced to double up, and a total of 14 electrons fit in the 4th energy level S sublevel. Now they go to the 5D, 1, 2, 3, 4, and 5 electrons. Now they'll pair up 6, 7, 8, 9, and 10 electrons. I've now found a home for 80 electrons. I need to get to 82, so I simply mark 2 arrows to give me 82 electrons. And that is how we do our orbital filling diagram. Once again, I'm going to do the same process that I previously did. I'm going to observe what I have here, and I will simply write it up above. I have a 1s2, followed by a 2s2, 2p2, 3s2, 3p6 with 6 electrons, a 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, and then 6p2. And that is the full electron configuration for lead. If I want to make my life easier, I would use an abbreviated format for this electron configuration. The previous noble gas for lead, if I pull in my periodic table, lead is here. My previous noble gas is atomic number 54, xenon. So I will go to xenon, put it in my brackets, and that was in the 5p category. So that is where xenon is at. And I write everything after xenon, which would be, once again, 6s2, 4f14, 5d10, and 6p2. And that is the abbreviated orbital filling diagram, or the abbreviated electron configuration for lead. So I hope you are able to identify the probable placement, I guess I need a typo there, the probable placement of electrons while an atom is in the ground state. I hope that you are able to recognize the pattern in which electrons fill orbitals within a sublevel, as well as be able to identify the electron configuration for an element and to complete an orbital filling diagram. Thank you so much for watching. I hope you have a wonderful day.